in our last lecture, we did few equations related to intrinsic semiconductors, right? Then the next part comes is doping. What is doping? It is the process of deliberately adding impurities to pure semiconductors, that is intrinsic semiconductors, to enhance their electrical conductivity. So what was the structure like? So you have written the definition, I guess I'll repeat it again. It is the process of deliberately adding impurities to enhance electrical conductivity of pure semiconductors slash intrinsic semiconductors. Now the structure of intrinsic semiconductor is like this, right? Based on the same fact that it has a valency of 4. We took the example of silicon. So this is how structure would look like. Now you must also remember what was causing the formation of holes and electrons. Both electrons and holes are actually not present initially when the system is in stable state, but even if the slightest hint of energy is acquired by those electrons which are forming 4 bonds, for example this silicon atom has 4 bonds with neighboring 4 silicon atoms, so this electron will actually jump from its space and it will get free. So this electron will be called conduction electron, and this will be free to move anywhere. That is what causes current, that is free electrons, and the void gap of electron will be called holes. So if an electron is jumping from, suppose, this hole to this hole, that means this hole is actually going that side. So that is why there are two kinds of different electrons, there are two types of different charged particles and two different currents. That's why we did equations for it. Now, right now, what if a pentavalent electron, a pentavalent atom has been added in this structure? For example, we have added a pentavalent impurity. This thing has a valency of 5. So what will it do? 5 valency means it will form 4, it will have 5 extra electrons. That means 4 electrons are going to they will make 4 bonds from 4 silicon atoms, but 1 electron is going to remain free. So this extra electron is an added benefit of adding pentavalent electron, right? Or pentavalent atom, not electron. Pentavalent electron would be a wrong word. Pentavalent atom. So, or I'll just simply say pentavalent impurity atom. So with the addition of each impurity atom, you are getting an extra electron in the whole system. That means, what if you add 1 mole of impurity atoms? By adding 1 mole, you will get 6.023 into 10 to the power 23 free electrons. That means huge number of electrons are already present in the system, and in addition to these extra electrons, you will also get these electrons which are creating holes. So in this case, number of electrons is way greater than number of holes. So that is why this kind of structure or this kind of semiconductor is called P type, right? This is P type, positive type. See, this is number of electrons is greater than number of holes. Number of electrons, that is negative charge, is way greater than the positive charge. So it must be what? N type. N type semiconductor, right? So what could lead us to form the P type semiconductor? N type is by adding a pentavalent impurity. So by adding a trivalent impurity, if you add a trivalent impurity atom, you will get an extra hole in the circuit. For example, this structure would be something like this. This is an X impurity atom, and trivalent means it will be having 3 bonds but 1 hole, right? There is 1 hole present in the system. So you can say that with the addition of every impurity atom, you are getting an extra hole in the system, due to which number of holes are greater than number of electrons, and such kind of formation will lead you to P type semiconductors. But what do we do by forming these two different kind of semiconductors? Here number of holes is greater than number of electrons. So what do we exactly do by forming these two type of semiconductors? See, this is the same point which I was telling you in our last lecture, that the semiconductors have a unique property, that their conductivity lies in between that of in solids, insulators and conductors, and on the basis of this, they lead us to form various type of different electronic or digital parts of the circuit called diodes. Now this n-type and p-type semiconductor actually led us to make diode, and the formation of diode itself was a great achievement when it was done. So what is a diode? The full name of diode is actually PN junction diode. This PN junction diode is not formed by taking a P diode, a P type of semiconductor, N types of semiconductor and add in the MEC. No, we do what? Suppose this is a P type semiconductor, we wafer N type and we melt it on one part of P side, and then it will become a PN junction diode. Basically what we take slices of N type or wafers of N type and we diffuse them into a P type semiconductor. So that is how it becomes a PN junction diode. But what exactly happens when you tend to form, and when you try to form a PN junction diode by this technology? See, I have taken for convenience, let us suppose that this is a PN junction diode, where we have, this is our P side and this is our N side. We have just combined P and M. What will happen? As such, there is no boundary, right, between P and N. Why there is no boundary? Because same type of charge are present in both P and N. The only difference is, see, P also have holes and electrons, N also has holes and electrons. Only difference is P will have more number of holes and N will have more number of electrons, right? But otherwise, what do you call if a semiconductor, suppose in this P side there are more number of holes, right? Let me draw it out. More number of holes, but this does not mean that it has absence of electrons, right? It do have electrons as well, like these. So these are called majority charge carriers and these are minority charge carriers, as the name suggests. And in N types, number of electrons are way greater than number of holes, right? So there must be some holes as well. Now what happen after we do this kind of formation? These holes are positively charged, these electrons are negatively charged. So obviously they are going to do what? They are going to attract each other. So at the junction part, there will be attraction between the neighboring electrons and holes, and what will happen? They are going to, a hole is a vacant space of electrons, so electron is ultimately going to jump and fit into the hole and it will create a neutral region, right? For example, this electron goes into this hole, so there will be a neutrality present here. So this part is going to get neutral, but otherwise what is happening here? Electrons and holes are recombining. But will this process stop? No, it's not going to stop. Why? I'll tell you. There is still a majority of positive charge here, majority of negative charge here, so there must be quite a force of attraction between them, and the force will keep on diffusing from one region to another. That will cause this central depleting layer. Depleting, why? Because there is no charge here as such, there are combination of charges here. This depleting layer, or so we are going to call this region as depletion region as well, or you can also call it as neutral region, right? So this neutral region is going to extend, it will keep on increasing. But what exactly is happening inside a neutral region? Electrons are coming from this part to that part. So when then electron moves, it actually creates a hole, right? So you can consider that they are creating positive holes where they are going and they are here. But otherwise this is a neutral region, because as such there are no free electrons or free holes. They are all recombined. It's just the way they are moving. The majority of positive charges are here because of the movement of electrons, and electrons are getting saturated or they are getting stored at this point. Now due to this, if any more electron wants to go to or diffuse to this region, they have to overcome the accumulative repulsive force given by these all these electrons which have accumulated, right? Similarly, if one more hole wants to diffuse from this region to this region, they will have to overcome the repulsive forces offered by these positive holes. So what exactly is happening? This depletion region is acting as a fictitious battery, a fictitious potential, or you can call it as potential barrier, due to which the migration of charge from one region to another actually stops. Migration will happen again when there is an outwards force which is opposing this depletion region, because right now it is acting as a fictitious battery. So this is what is happening, the negative terminal here, positive terminal here. So this region, which is known by two names, one is what? Neutral region, and another is depletion region. This will also be called as a new name called potential barrier, right? So the neutral or depletion region is acting like a fictitious battery, and it is called potential barrier, due to which there is no further migration of charge from one region to another. So when we started creating a PN junction diode, we just left P and N on a side. P was at one side, N was at one side, but actually what happened, this potential barrier is automatically getting created. So this makes a unique property of diode, because on the basis of this we can use diode in a different ways, in very different ways. For example, diode has a directional property. Diode can allow current to pass through it only when current is going in one direction, not the other. How? We are going to read it, we are going to study about it, but this doesn't happen in case of resistor, this doesn't happen in case of capacitors. So diode only has this property, and that too because of that special property of semiconductor, that is the temporary conductivity, right? That is the word. So what is a PN junction diode? PN junction diode is a device, or you call it an electronic digital circuit part, which allows a directional flow of current, right? And how is it formed? It is formed by diffusing P type wafers into N type semiconductor, or N type wafers into P type semiconductor. What else? What is potential barrier? Potential barrier is a neutral or depletion region formed, which behaves like a fictitious battery. When a PN junction diode is formed, it opposes the further migration of charge from one region to another. This is all about it. So how do we represent a PN junction diode? PN junction diode is represented like a triangle and a rod. This is the symbol of PN junction diode. This part is P, this part is N. So how do we use a PN junction diode? So PN junction diode, the first thing we are going to study is applications, and in applications, first thing, okay, before moving on to applications, let us bias. Biasing means working of semiconductor PN junction diode. So let's study a bit about how does it work, how does it behave, working of a PN junction diode. For that we have to actually connect it to a cell an outer potential difference which has to be greater than the inner potential barrier value, so that it is going to, then only we will be able to see how it works, right? So I'll be making two different diagrams. One, I'll be representing just a circuit diagram here. I have to apply a varying voltage. So instead of going through all that rheostat and then connecting it to the battery, this is a variable battery, right? And same thing, I am doing it like this. I am drawing my part here. This is our potential barrier region. Here we have P side, and here we have N side. In P region we have some N, in N region we have some P. These are minority charge carriers which do not affect the value of current at all. This is the rest of the circuit. Varying voltage. Okay. How do you measure the current flowing through it? You measure the current flowing through it by implying an what? An ammeter. Similarly, how do you measure the voltage? By using a voltmeter across the ends. So there is ammeter, there is voltmeter as well. Where do you apply, where do you put the voltmeter? to know the voltage or potential difference across it, you have to use it across, right? Now, what will happen? See, the graph will explain you everything. What will happen? This is a current versus voltage graph for a p-n junction diode. We already have some value here, a fixture's battery working here, which is opposing these charges to go from one region to another. Now this is in a stable state p-n junction diode, because if in the presence of external battery this charge wants to go from this region to this region, it has to overcome the value of this potential barrier. So the value of applied voltage has to be greater than the value of the inner potential barrier, obviously. Now this is positive, this is negative, so all these positive gets repelled by this positive and negative gets repelled by this terminal. So the value of potential barrier automatically get decreased, or you can say that this potential barrier region, which was initially this much, shrinks to this much region, and since its value decreases, there is a very easy flow of charge from one region to another. But now many students go through this doubt that what if now, because of this external help, these charges are they can easily overcome this value and they can jump from this region to this region, or they can migrate from this region to this region. So are they going to get nullified again and they are going to increase the depletion region? No, because right now all these charges are under the influence of this external battery. So they are just going to move from one region to another, and then suppose I am talking about this particular positive charge, it will go from this region to this region, but right now it is under the complete control and influence of this battery. So it will move according to this wire, it will go inside this battery, there will be a breaking of covalent bond here, and the same charge will be liberated from this side and it will enter here. So the circulation of charge and the conservation of charge is getting balanced, or it's a constant thing. We know the conservation of charge, right, that charge remains constant. So in the presence or influence of this battery, charges are migrating from one region to another just to accommodate or just to make the flow of current. So now this is how it works. Voltage, even if you increase the voltage, the value of current does not increase. It is in milliamperes. The value of current will not increase unless and until the external voltage is at least equal to or greater than the internal voltage. Once that voltage is achieved, this part is called knee voltage. Once this value is achieved, current increases almost linearly with voltage, and that is why we say that p-n junction diode is a non-ohmic device. It do not follow the Ohm's law, because you can see the graph is not a straight line. So this is not following Ohm's law at all. So this is a non-ohmic device. So what are the main points? Current do not increase with voltage till the point knee voltage achieve. What is knee voltage? That the value must be equal to the potential barrier voltage. Once that value is achieved, the current starts increasing almost linearly, right? Now what will happen if I connect negative to this positive part and positive to the negative part? Will that make any difference? So yes, that will make any difference. So this part of connecting the circuit positive to negative is called forward biasing. This is called forward biasing of p-n junction diode. So if there is a forward biasing, there must be reverse biasing again. So what will happen in case of reverse biasing? Let's redraw the diagrams. In case of reverse biasing, we connect the positive terminal of our battery, that is external battery, with the negative n part. This was our potential barrier. These are our positive charges. These are our negative charges with some minority charge carriers as well. These minority charge carriers are sometimes not represented in your books, so but you have to keep that in mind that these charges are still there. This time negative is towards p type and positive towards n type. So what will happen? This negative charge will attract all the positive towards this end, and this positive part will attract all the negative charge towards this end. Moreover, they are also supporting the potential barrier, right, voltage. So what will happen? It is going to increase the value or the area or the volume of this potential barrier region. So this time the potential barrier region increases. So will there be any flow of charge from one region to another? No, not at all. But what will happen if you keep on increasing the voltage, that is called reverse bias voltage? What will happen to the reverse bias current if you keep on increasing reverse bias voltage? There will be almost no current even if you increase the voltage by a very large part. That is why this current is mentioned in microamperes. But there will be a point when there will be a sudden flow of charge across the region, that is all this positive charge, when this value is too high for them to control, all the positive charges are going to instantaneously drift towards this negative terminal through this side. That means this negative charge are going through this side, this positive charge is going through this side. That is called a breakdown. And in that point, what will happen? There will be sudden flow of current in the PN junction diode. This part is called, either you call it Zener breakdown voltage or you call it avalanche breakdown voltage. Either avalanche breakdown voltage or Zener breakdown voltage. At that point, the circuit undergoes a breakdown state where all the charges instantaneously move from one region to another across to go through battery, and we do not want this phase to actually happen. So for example, there is a diode whose reverse breakdown voltage is calculated as 10 volt, that this diode will undergo, or it will behave in a breakdown voltage, or it will undergo breakdown value for where voltage values above 10 volt. So we will not use this diode where reverse voltage is going anywhere above 8 volts. That means it will never go in the breakdown phase. So we are not going to experience this part. So what do we want from a diode? We want diode to conduct easily when it is forward biased, and we want it to not conduct at all when it is reverse biased. That is why it will become a unique type of device, not like resistors and capacitor where there is a both side flow of current. This case, diode is working only when a current is going in a particular way, a particular direction. Other way around, current will not pass. So it is behaving like a temporary switch. You can't call it switch because switches are actually closing it down and opening the circuit. It is behaving like a controlling the current according to the direction of current, right? So where do we use this property? Now comes the part applications of PN junction diode, and the first application we are going to do is rectifier. These are applications, and we are going to do rectifier. What is a rectifier? Rectifier is a device which converts AC voltage to DC voltage. This converts AC to DC. How does it do that? See, rectifiers are of two types, half wave rectifier and full wave rectifier. You will understand it from the diagram. We have a source of AC which is to be converted into DC. So we transferred it using transformer. You know, this is the symbol of transformer. We have done it in AC circuits. These are supposed to be ellipticals or like this. These are wirings, like coilings basically, right? So this is the symbol of transformer. Here we have a diode, and then we have a load resistor R, variable one, RL, across which we are taking output. This is where we are going to take output. So what will happen here?